What I'm going to talk about today is joint work in progress with Ralph Klasse, who's also in the audience. So I noticed when I was done preparing that the introductory material is sort of quite a lot of the talk. So it's a relatively large proportion of the talk. But so I hope that this won't bore most of you. But since the new stuff that I'm going to say doesn't really make much sense if you don't know the introductory material, I think it's probably worth it, hopefully worth it. So I want to start talking about material that is already known for quite a long time, that involves first modular classes of Lie algebroids, and then specifically the modular class or modular vector field as a representative of a Poisson structure. So if you want to read something about this, there's a nice survey article by Yvette Grossmann-Schwarzbach, Poisson manifolds, Lie algebroids, modular classes, a survey where a lot of the basic things that I'm going to say at the start are explained. So the modular class is a particular characteristic class we can associate to any Lie algebroid, and it's one example of the characteristic class associated to actually every Lie algebroid representation. So let's also fix a real line bundle. So if you want, you can also do all of this complex, but I'm going to mostly stick to explaining the real case because it's a bit easier, but almost everything I say will generalize relatively straightforward to a complex Lie algebroids, complex representations. So L is supposed to have a Lie algebroid representation. So what's that? That's a Lie algebroid connection, so connection of A on L that is flat. So the important properties to keep in mind for this kind of object. First of all, okay, this is an A connection. So what this means is that it has a Leibniz rule for functions. Rho is the anchor of the Lie algebroid. And then I said it's flat. So that's this relation. Vanishing, this is the vanishing of the curvature, and it also immediately shows why we would then call this a Lie algebroid representation, because it's compatible with the Lie bracket on A. So now for the specific case we're considering here, where it's rank 1 representations only, so always line bundles, we of course have just one non-vanishing linearly independent section. So let's assume mu is a section or local section of L that's non-vanishing. We do not have to assume that this exists globally, which of course, I mean, that would mean that the bundle would be trivial. And now we know that when we act with this Lie algebroid representation of mu, whatever we get is again a multiple of mu, because we're in a line bundle, and this is linear, will be linear in A. So in fact, we can write this as the pairing of the Lie algebroid element or the Lie algebroid section A with an element or a section in the dual of A. So this depends on mu, and it's a section of the dual of the Lie algebroid. And this would be called the characteristic section associated to this Lie algebroid representation. Okay, and now what you can work out is that, am I going to write all of this? maybe not, but so A star and its alternating tensor powers are equipped with a differential complex as the dual of a Lie algebroid. So we can consider the derivative of this object A mu within this complex. So that will be a section of twice A star, so A star 2 forms. And so we can put in two Lie algebroid elements, and that's just defined this way. And now, if you work this out, so this is actually equal to this expression, which of course is just the curvature of the Lie algebroid connection, which we assume to be 0 to get a representation. So that's an important property of this characteristic section, that it is in fact always a closed element in the complex associated to the Lie algebroid, and thus defines a class in the first Lie algebroid cohomology. And as I said, the section itself depends on mu, but this class does not. So instead of mu, we could also have f mu, where f is some non-vanishing function, and then what we get is that this is the same as a original a mu plus rho star d log f mu. So as you can see, the characteristic section will only change by something that's exact in the Lie algebroid complex, and so this characteristic class is well defined as a class in the first Lie algebroid cohomology. So now what we mostly want to be concerned with in this talk is a particular representation that exists for every Lie algebroid, the modular representation. And that's a representation of A on the line bundle determinant of A. So by determinant of a vector bundle, I mean its top alternating power, tensor determinant of the cotangent bundle. And so if lambda tensor mu is again a local non-vanishing section, then the representation is given this way. So we take the Lie derivative induced on det A just by the Lie bracket on A. And in the second term, we take the Lie derivative of the top degree form with respect to, well, the anchor of A. And note that, of course, each single term here will not be a representation or a Lie algebroid connection, because the connection needs to be linear in this element, right? C infinity linear, and each of the separate terms is not, but the contribution that will contain df, if I put in function f at the bottom here, in those two terms come with opposite sign, and so they will cancel. So this combination is indeed a Lie algebroid representation. Okay. So now we want to go to the case where the Lie algebroid is the Lie algebroid associated to a Poisson structure. So the cotangent bundle equipped with the Poisson bracket you all know and the Poisson bivector as the anchor. Now, the modular representation, which I just wrote down, will simply be the determinant of the cotangent bundle squared. And in fact, we can also, in this particular case of the Poisson structure, just define a representation on the top degree forms whose square, so tensor product with itself, will then be the modular representation on this squared bundle that I just showed you on the page before. So on T star M, the representation is this, and probably, again, most of you have seen this at some point. So this is equal to this expression. So in the second expression, you can very explicitly see that it's linear in Xi. And then, of course, here we get the modular section of the Poisson modular representation. And since the dual of the Poisson structure Lie algebroid is simply Tm, so this is the modular vector field. So now, yeah, I guess when you actually go and calculate with this, you have to be a little bit careful. So this modular vector field will then be 1/2 of the modular vector field that you get if you use the square, but I mean, they're directly related to each other, so it's not a big deal. And yeah, as we all know, of course, the modular vector field then defines the modular class inside the first Poisson cohomology. And this is an obstruction to the existence of a global volume form on the Poisson manifold that is invariant under Hamiltonian vector fields, which I think when you come from the perspective of Poisson geometry, that's how it's often introduced. So you would write it directly like this. Which is, of course, the same expression as above, just specialized to exact one forms. Okay, now I'm going to talk about the object that sort of inspired this whole project, and that is the modular foliation of a Poisson structure. So as far as I'm aware, this was first named or explicitly discussed in the paper by Gualtieri and Pym, Poisson modules, and degeneracy loci. So we're all familiar with sort of the ordinary foliation that's associated to every Poisson structure, which is simply the image of the cotangent bundle under the anchor. Now we can define this additional foliation, the modular foliation, which is that, oops, sorry, not a direct sum, plus whatever is generated by the modular vector field. And this is well defined because when I change the local non-vanishing top form that I'm using to define the modular vector field, then as we just saw, the modular vector field will just change bi-Hamiltonian vector field, which is of course already contained in the first component f pi of the foliation. So the foliation itself is independent of whichever local modular vector field I use to define it. And yeah, this second foliation that is also associated to every Poisson structure has not been studied particularly intensively. So not that much is known about its behavior for general Poisson structures. So of course, we can see that a lot of the time, the modular foliation and the ordinary foliation of the Poisson structure will actually agree. So for a lot of Poisson structures that we like to study, the modular vector field is almost everywhere tangent to the Poisson foliation. So then there are only a few places where the modular foliation has an additional direction compared to the original foliation. So here's an interesting fact that we do know about the modular foliation. So this is a result of Ralph in his preprint Poisson structures of divisor type. So there Ralph studied these Poisson structures that are also known as almost regular. So where the foliation can be expressed as sections of a Lie algebroid. And then it's particularly interesting to look at Poisson structures that are sort of Lie algebroid type, in the sense that they are push forwards of a Poisson structure on a Lie algebroid. So let's assume we have a Lie algebroid and a Poisson structure on the Lie algebroid, so a section of the alternating square of A, which is Poisson in this sense. And we then have a Poisson structure from pushing forward the pi A. And if we consider its ordinary foliation sitting inside the modular foliation, we can also show that that always sits inside the foliation given by the Lie algebroid A, so the image of the anchor. And in fact, in sort of well-known examples such as log Poisson or log symplectic structures, this second inclusion is actually an equality. So the modular foliation in that case is equal to the foliation given by the Lie algebroid. And so yeah, I think this is sort of one example that raises interesting questions about yeah, what extra information the modular foliation contains compared to just the ordinary foliation, and how they behave in general. So for example, when is the modular foliation also a projective foliation, so sections of a Lie algebroid? So even if f pi is projective, that does not mean the modular foliation has to be. We don't know how it is vice versa. We also don't know when, sort of for almost regular Poisson structures, when this second inclusion is actually an equality. And so yeah, this kind of thing is what prompted Ralph and me to yeah, look at this more and yeah, study the modular class. So before I come to what I have actually done as a new thing, I am going to talk about another object related to the modular foliation that's already been known for a while. So this comes up a lot.
Ask a question?
Yes.
In terms of concrete examples, if it's a dual of a Lie algebra, are these foliations always the same, or only if the Lie algebra is unimodular or something?
So certainly whenever it's unimodular, then they'll be the same. So for Lie algebra, wait, what does the modular vector field do. So so for any regular regular Poisson structure, they're the same, which of course the Lie algebras are not. I haven't actually, so where does the modular vector field point for a Lie algebra? I haven't thought about that.
Okay, but yeah, if they're the same for regular, then suggests probably like by continuity, more or less. Okay.
Yeah. So what do we know is that whenever they are potential non-equalities of the modular foliation and the ordinary foliation happens whenever the Poisson structure degenerates. So at degeneracy loci, this can potentially so this potentially happens. Although of course, since the modular vector field is a Poisson vector field and degeneracy loci are strong Poisson submanifolds, we also know that the modular vector field has to be tangent to the degeneracy loci, but the foliation can differ. So maybe I should, one sec, maybe I should give this example with the log symplectic, just so we can see an example where the modular foliation is different. So let's have this really simple log Poisson structure like this. Then the f pi is this, right? And the modular foliation instead is this. So it has this additional term del and del y even at x equals 0, which the ordinary foliation does not have. So we can see that precisely at the degeneracy locus, this foliation gains an extra direction, and that is in general how the behavior works somehow.
Oh, thanks, very helpful.
Okay, so yeah, now I want to discuss an object that is very closely related to the modular foliation, namely whenever we have a Poisson module, so a representation, a Lie algebroid representation of the Lie algebroid associated to the Poisson structure, then we can get a Poisson structure on the total space of this line bundle that carries the representation. And most of you also probably have seen this, or at least have seen instances of where this happens. So again, let this be a line bundle. So with representation, flat representation, or flat, okay, representation or flat connection. Sorry, I'm mixing up the two things. Of the Lie algebroid. Then we have the Atiyah algebroid associated to the line bundle L. So the Atiyah algebroid, recall, is the bundle whose sections are derivations on the vector bundle, and this always fits inside such a short exact sequence. So here are the derivations. They get mapped to the underlying vector fields, and the kernel of this morphism is precisely just endomorphisms of the line bundle, or of the vector bundle in general. And in this case, because L is a line bundle, this is actually just trivial. And what's important in this case is that derivations of a vector bundle are always in one-to-one correspondence with linear vector fields on the total space of the vector bundle, which hopefully also most of you have seen. So by linear vector fields on L, what we mean is sort of vector fields of the form so if xj are the base coordinates and y is the fiber coordinate, then what we should have is something like this. So this is what locally what a linear vector field looks like. It has the base directions, and then the fiber direction only comes up with a linear dependence on the fiber coordinate, and anything that's not linear can only depend on the base coordinates. And yeah, these things are in one-to-one correspondence with derivations on the line bundle. And under this correspondence, the generator of the endomorphisms, which in this case is just a trivial bundle, is the Euler vector field. So here this is generated by the Euler vector field, which in this local coordinates is just y delta y. So now choose a fiber metric for L. So just fix some fiber metric and local trivialization, so that in each open neighborhood of the trivialization we can pick sections of norm 1, so lambda, like we get this local basis of length 1 sections. Then this choice, once we've made this choice, that induces a flat connection on L, by which I now mean a flat tangent bundle connection, so connection in the conventional sense. So precisely this connection is then precisely so that the local sections lambda are flat. And because this is a real line bundle, that actually defines a global flat connection. And that's of course the same thing as saying we have a flat splitting of this short exact sequence. So I'm going to call this the M connection nabla hat, and I hope that can be told apart from the Lie algebroid connection, which is just nabla. So we can use this to write the Lie algebroid representation on a general section of L as this. So lambda are the local sections of length 1 that we fixed. This is the characteristics section with respect to the lambda. And then for any other section L, this is what the connection looks like. That is relatively easy to work out. So basically, the Lie algebroid connection is written in terms of the flat TM connection and the characteristic section. This is what I just did. This is all true for any Lie algebroid for any rank 1 representation. But now we want to specialize to the case again where it's actually Poisson. So in that case, remember we had that the characteristic section is actually a vector field. And now we can use the construction we just made to define the following. So we define a Poisson structure, which you can either view as a section of the alternating square of the Atiyah algebroid, or as a Poisson structure on the total space of L, which will then be linear, and which looks like this. So tilde denotes the horizontal lift with respect to nabla hat. This is a bivector field, so we can also lift that with a horizontal lift. We can also lift the modular vector field, and then we can wedge it with the Euler vector field. And now this defines a Poisson structure. And in fact, this Poisson structure, the way we've set it up, is invariant under the choice of local sections that we made. So if we pick, where was it? If we pick a different fiber metric, we will get different sections of length 1, which will give us a slightly different flat connection. And these changes work out in precisely such a way that when we then use these modified objects to define the horizontal lift and the modular vector field, the differences cancel, and this Poisson structure actually remains invariant. So as I said, this already comes up in these two papers I wrote at the top. And now what we see is that the foliation that is associated to this Lie algebroid Poisson structure pi hat, so this is the foliation. We take the dual of the Atiyah algebroid, pair it with pi hat to get something in the Atiyah algebroid again, and map that to Tm, so that's the foliation. And that is precisely the modular foliation of pi. So the pi hat is a Poisson structure on the module that encodes the modular foliation. Okay, and this is not that hard to compute. So if you like, so at L star with our choice of splitting is split into T star M plus E, where E is the element that pairs to 1 with the Euler vector field and pairs to 0 with Tm. So this is the splitting induced on the dual by the choice of local splitting of the Atiyah algebroid. And then we get that if we plug these two components into pi hat, this is what we get. So you can see that when in turn we go and we project this down to Tm, which kills the Euler vector field, so the second part goes away, then the image of this will precisely be the modular foliation. Okay. As I said, so this is at least in certain instances quite well known. So in the paper by Gualtieri and Lee, symplectic groupoids of log symplectic manifolds, they actually do this whole construction. But in particular, there is a case where you see this very explicitly in an example, namely the normal bundle to the degeneracy locus of a log Poisson structure. That comes with a representation of the Poisson structure on the degeneracy locus, and then thus there is a Poisson structure on the total space of the normal bundle, and this is precisely the linearization of the log symplectic structure around the degeneracy locus. So that is an example of where precisely this Poisson structure comes up. Okay, so what I now want to do, and what is new, is look at what happens when we pass from Poisson structures to general Dirac structures. So for simplicity, we're going to consider Dirac structures in the standard real Courant algebroid, and we're going to consider real Dirac structures, but this works in exactly the same way in any exact Courant algebroids, and you can do things slightly differently to also get the same result for complex Dirac structures. So again, we choose a representations, a rank 1 Lie algebroid representation of D. So D is a Dirac structure, just of course has an induced Lie algebroid structure, and then it always has this modular representation. So if you want, you can think of L as being the modular representation. We again fix a fiber metric on L, local sections of norm 1, and we also have this induced Tm connection that is flat that I mentioned before, such that we can write the Lie algebroid representation in this way, which is what I just did on the page before. And so now what we have is that the characteristic section well, it's in the dual of the Dirac structure, so D star. And D star can be identified with a maximal isotropic complement to D in Tm plus T star m. So we just fix one of those. Note that F, the complement, is not necessarily itself a Dirac structure. So there are Dirac structures that do not admit a complementary Dirac structure. However, you can always get a maximal isotropic complement that is then maybe not integrable. So what we can now do is view the characteristic section, which is a section of the dual of the Dirac structure, as well a section of F, and thus actually sitting inside the sections of Tm plus T star m itself again. So why do I want this? Because I essentially want to also consider something like a modular foliation and something like this, well, where we earlier had the Poisson structure on the total space of the module, I now want to consider a Dirac structure for the total space or the ATIA algebroid of the module. And in order to do that, I have to have a way of viewing the characteristic section, which is normally just abstractly a section of the dual of a Lie algebroid. I need to have a way of viewing that concretely on the same footing as the sections of the Lie algebroid itself, which now we have both the Dirac structure as well as F, which we've identified with its dual, sit inside Tm plus T star m, so are a sum of a vector bundle and a one form in some way. So yeah, what we can now do is actually define the modular foliation for the Dirac structure, which is just the ordinary foliation of a Dirac structure. So rho being equal to just projection to Tm plus the projection to Tm of the characteristic section. And again, this is invariant. So invariant under the choices that we make, chiefly the choice of local section of L. Why is that? So as we've seen before, when we change lambda, A lambda goes to A lambda, well, and then the sign depends on exactly what the change is. So in my case here, it's now a minus. So minus d log f. But now I have to be a bit careful. I've chosen a particular complement to d. So this modified characteristic section should again be inside f, which this might not be. However, we can always add a section of d itself so that this thing is in f, this thing is in f, and so the whole thing, the modified characteristic section, is also again in f. And then rho of A lambda minus d log f minus del f is rho of A lambda minus del f. So the foliation again remains invariant because whatever we get to change this extra component was already in rho of d. Right. However, there is now a difference already to the Poisson case. So in the Poisson case, the dual of the Lie algebroid can always be chosen to just be the tangent bundle, right? So Poisson structures are precisely those Dirac structures that are transverse to the tangent bundle. And thus, the characteristic section can always be seen as just a vector field. And we do not have to project to Tm. Whereas in the general case, for general Dirac structure, there may be genuine information in the one form part of the modular section or modular class, so that when you do this procedure to define the modular foliation, you actually lose information about the modular class that is contained in its one form part. So this is a somewhat, or this is somewhat unsatisfactory, and maybe tells us that the modular foliation is not the object we should be looking at in the Dirac context, but instead we should be looking at the analog of the Poisson structure on the Atiyah algebroid, which will now be a Dirac structure. So what we want is to construct a Dirac structure d hat sitting inside this Courant algebroid, so Atiyah algebroid of L plus Atiyah algebroid of L star. This is naturally equipped with a structure of a Courant algebroid just by virtue of having the following Lie algebroid. So Atiyah algebroid of L, of course, comes with a Lie bracket and an anchor, which is the projection to the symbol. And we equip the dual with the 0 Lie algebroid structure, and then this is a Lie algebroid, which gives you a Courant algebroid. So how to construct this d hat? So I'm first going to do it in a very explicit way, and then I'm going to show you an easier description via spinners that is, however, less explicit. So I'm going to define a map tilde, which goes from Tm plus T star m to this new Courant algebroid that maps x plus xi to x tilde, where this is now horizontal lift with respect to the flat Tm connection I had chosen, plus just xi, where note that so T star m naturally includes into the dual of the Atiyah algebroid independent of any choice of splitting, so we can just put that in and include it that way. And then I'm going to define a lift on, first of all, sections of D. So delta is a section of D, and I'm going to lift that to D tilde plus the pairing of delta with the modular section times the Euler vector field. And then I'm also going to lift the characteristic section just somewhat differently. So that also gets mapped with this, gets lifted with this tilde map. And then I'm going to subtract capital E, where remember capital E was sort of the dual element to the Euler vector field. And then I'm going to consider the span of this. So d hat is the span of all these LD, and then it's in addition L of A lambda, which sits inside here. And I'm going to claim a bunch of things. So first of all, that I'm going to claim that this object is independent of any choices we've made. So what were the choices? The choices were the fibermetric G. I mean, so really the choice was just the fibermetric G, and then this induced the lambda, the nabla hat, the A lambda, the tilde. It's also independent of the choice of maximal isotropic complement, F. It is actually itself maximal isotropic in this Courant algebroid. For L, it is, so thus it's almost Dirac. It is also integrable, so it is in fact Dirac. And if I map it to Tm with the anchor map of at L plus at L star, I get the modular foliation of the Dirac structure that I discussed. Okay, and lastly, if sigma is the map from the T algebroid to Tm, so sigma at L to Tm, then sigma star defines a forward Dirac map between, so like this, that takes d hat to d. So really the object that contains the full information about the modular class of a Dirac structure is not the foliation inside the tangent bundle, but is actually this upstairs Dirac structure that is analogous to the upstairs Poisson structure we looked at earlier. And so I'm not going to prove any of these claims. They are mostly, once you somehow know how you need to combine all the different things that are not invariant to get invariant things, this is not too hard to do. So instead, I'm just going to show that in the case where the Dirac structure is Poisson, so is the graph of pi, the d hat is the graph of the pi hat that we had before. So in the Poisson case, this actually reduces to the known construction. And right, I had basically already written down what you needed to see this before, but I'm just going to write it again. So pi hat of just the one form xi was pi of xi tilde plus the pairing with the modular vector field. Pi hat of E, the dual element to the Euler vector field, was minus the modular vector field. And so the graph of pi hat is equal to pi tilde of xi plus xi v mu E and E minus, the span of this. And this is exactly what D was. So these kinds of elements were what you got from lifting the Dirac structure, and this was the element you got from lifting the characteristic section. So essentially, this procedure really just generalizes the Poisson case. Okay, as pretty much the last thing, I want to show the spinor for this, the pure spinor. So recall that every Dirac structure is equivalently defined by its pure spinor line. So D is equivalent to a line bundle sitting inside the combined bundle of all forms. And the integrability of D as a Dirac structure is equivalent to a local section. So rho is a local section of K that is non-vanishing, being equal to some A rho dot rho, where this is the Clifford action. So I'm sorry if anyone has not seen this, then this is probably too fast. So this section A rho, so this is not unique. So this is some section of Tm plus T star M. We can choose it to be an F, which was the complement. But of course, so really this is also a section of the dual of the Dirac structure. And here's a fact that is proved in, as far as I'm aware, unpublished work by Alexeyev and Xu. So it's a preprint called Derived Brackets and Courant Algebroids. Where the two authors show that, in fact, this A row is equal to 1/2 the modular section that we had earlier. Where now, of course, so this was defined with respect to a local section rho of the spinor line. This was defined with respect to a local section of the modular line bundle. So now we need to know that these are related in some way. And in fact, the square of the spinor line is isomorphic to this modular line. And so this equality here is if we map rho tensor rho to lambda. So if the local sections of these two bundles are related under this isomorphism, then yeah, whatever we get here for the integrability condition of the pure spinor is just 1/2 the modular section. And using that fact, we can see that this is in fact a local section of the pure spinor line for the d hat. So if you have this, so above I had this very explicit expression for what generating sections for d hat look like. So you can check that when you act with those on the spinor with a Clifford action, that those are precisely the ones that annihilate the spinor. And now you can check the integrability of the above d hat very easily, because so clearly d xi is just equal to 1/2 e wedge d rho, which is equal to 1/2 e wedge the original xi, and this already shows integrability of the associated Dirac structure d hat. So somehow starting from the spinor picture, that that part is much easier. So this is actually also equal to just a rho wedge xi, because 1/2 e minus a rho is in d hat. And so we can see that, well, actually the upstairs Dirac structure essentially has the same modular section as the original Dirac structure. So you can also make this whole construction for other representations of D that are not the modular representation. However, in that case, this thing with the spinor is much more subtle, because you do not have this straightforward relation between the spinor bundle and whatever other representation you might pick, but that can be fixed. And this spinor description is also the easiest way to generalize this to complex Dirac structure. So for example, yeah, I'm interested also in the modular class of generalized complex structures, certainly. And yeah, then this approach, I think, is the right way to do that. Okay, I'm basically out of time, so maybe I'm just going to say a few last words. Yeah, about the modular class of Dirac structures. So we know what it is for Poisson structures, and in some sense, the opposite end of a Dirac structure compared to a Poisson structure is a regular foliation, or just a foliation. So at every point, a Dirac structure can be viewed as a subvector space of the tangent space with some two-form just defined on the subvector space. So in the case of the Poisson structure, it's the subvector space that's the image of the Poisson bivector. and the 2 form is the symplectic form on the symplectic leaves. So a Poisson structure is a Dirac structure where this 2 form is precisely non-degenerate on the leaves, whereas just, a regular foliation is a Dirac structure where we have a subspace and then a 0 2 form. So in that sense, Poisson structures and Poisson structures and regular foliations are at the opposite ends of what Dirac structures can be. And this is also seen in their modular class. So for Poisson structures, the modular class is a class of vector fields, so it's contained in the Poisson cohomology. In the case of regular foliations, the modular class is purely a 1 form. So that is the extreme case where there is no meaningful vector component at all. And so in particular, you never get any interesting modular foliation, even if the modular class is highly non-trivial, because, well, it would just be projected away. However, you do get a non-trivially different d hat. So for regular foliation, the modular class is actually what's known as the Reeb class in the study of regular foliations. So there's quite a lot of literature on the Reeb class. In particular, there's a little result that the Reeb class of the foliation that underlies a regular Poisson structure is equal to the modular class of the Poisson structure. And if you now know this Dirac picture and you know that, well, okay, you could just look at the modular class of the Dirac structures, then then this fact actually becomes completely obvious. So it is completely obvious to see that for regular Poisson structure, the modular class is just the modular class of the underlying foliation. Yeah, and so I think there's still a lot of interesting things to discover about general Dirac structures, and in particular, maybe in the complex setting and for generalized complex structures. And yeah, I could have told you more things, but I'm out of time. So thank you very much for your attention.